So here are the solutions worked out to 7, 10, 12, and 31 from pages 214 to 217. So let's take a look at number 7. Optimal dimensions. You are planning to make an open rectangular box from an 8 by 15 inch piece of cardboard by cutting congruent squares from the corners and folding up the sides. What are the dimensions of the box of the largest volume? So we want to maximize volume that we can make. And what is the volume? So I start by just drawing some pictures. So this is kind of like what we're starting at. We have a rectangular piece of paper here, or cardboard, and we're cutting out these squares. So pretty much like what's happening here is, imagine where we were to cut these out, we would get like a little perforation right here. And this is where we would fold. So these flaps on the sides, once we cut out the corners, become the sides of the box. So that's what I did right over here, was I just kind of drew the box sort of formed. So originally it measured 8 by 15, but if we're cutting off x inches from each end, that now becomes 8 minus 2x, which would be our width. 15 minus 2x would be our length, and then x would be the height of the box. So the formula for volume of a box here, or a prism, is just going to be length times width times height. So I just multiplied the three dimensions together and then expanded it. So I called it v of x, and it ultimately turns into 4x cubed minus 46x squared plus 120x. So we're trying to maximize volume. So now we just want to find the derivative of this. And it becomes 12x squared minus 92x plus 20. So because we're able to, we can factor out a 4, and then we're able to factor what remains. Now keep in mind, our dimensions, our answers need to make sense here. So it's, our first derivative is never going to be undefined. But solving this, we get x equals 5/3 or x equals 6. Now if x is equal to 6, this isn't going to work here, because we would get 8 minus 12, so 6 isn't going to work. And even if we still used the 6, so I'm using the second derivative test, this is where it's going to be most beneficial. When I substitute in a 5/3, I would know that I would get a negative value here. So we're going to be concave down, and that's where we're going to get a relative max. Even if I tried the second derivative when x is equal to 6, we're going to be concave up, and we don't want that anyway. We're not trying to minimize volume, we're trying to maximize volume. But again, just keep in mind, this part here is very important. This is our justification, so you definitely need to write this out just as it looks. Then we just want to find the dimensions here. So when x is 5/3, our length is going to be 35/3. This is all in inches. And our width will be 8 minus 2 times 5/3, which gives us 14/3. And that would make our height 5/3. So the max volume is, if we multiplied all three of those together, and we could leave it like this, you could turn it into a decimal. But here's our volume in cubic inches. When the length is 35/3 inches, the width is 14/3 inches, and the height is 5/3 inches. Let's take a look at number 10. This is named the shortest fence. A 216 square meter rectangular pea patch is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. Well, there's a lot going on there. Let's take a look at what the picture could look like. So here's our rectangular patch, and then we're kind of dividing it here. So we're making a length here of x to be parallel to the other two sides. And I'm going to call all of those x. Now the area of this entire rectangle, I just worry about side times side. So I'm just going to call the area x times y. And I want to get all this in terms of x. So if the area is 216, 216 would equal x times y. Solve for y in terms of x, so y is going to equal 216 over x. So just reading the rest of this, what dimensions for the outer rectangle will require the smallest total length of fence, and how much fence will be needed? So that tells us we want to minimize perimeter. So perimeter here is going to be 3x, because I've got 3 x's plus 2y, and then I'm substituting the 216 over x in for y. And then that just turned into 3x plus 432 over x. Let's find the first derivative over here. So that would just give me 3. Again, we could treat this as 432 x to the negative first, and this is what results. So where is that going to equal 0? We can multiply everything here by x squared. So we get 3x squared minus 432 equals 0. 432 divided by 3 gives us 144. Now we only want a positive value, so x equals positive 12 only. It's undefined when x is 0, but x has to be greater than 0 because we're dealing with a measurement here. So again, we want to minimize perimeter. Let's do the second derivative test for extrema. This will turn into a positive 864 over x cubed when we take the derivative of this. And when we evaluate that at 12, that's still going to be positive, so that tells us we're concave up around x equals 12. Therefore, we have a relative min at x equals 12. So that tells me x is going to equal 12 meters. Y is going to be 216 over 12, which is 18. So the P patch will measure 12 meters by 18 meters with a 12-meter divider. The total amount of fencing would be 72 meters. And that's just finding all of the perimeter here plus the section where we divide the patch. All right, next we have number 12, catching rainwater. So we have a 1,125 cubic foot open top rectangular tank with a square base of x feet on a side, y feet deep, which is to be built with its top flush with the ground to catch runoff water. So let's see what this picture could look like. So it's just pretty much a box shape that we're looking at here, but it has a square base and it's going to be y feet tall. The costs associated with the tank involve not only the material from which the tank is made, but also an excavation charge proportional to the product XY. So luckily they give us the cost function. We don't have to try to come up with that, but we're trying to minimize the cost. So I want to get everything here in terms of x. So over here off to the side, because question A, if the total cost, which is given to us here, what values of x and y will minimize it? So I'm going back, if we're trying to minimize cost, but we're also dealing with volume, it's kind of like our helping function. So volume would be calculated by x times y, and we know the volume of this tank is 1,125 cubic feet. So I solve for y in terms of x. So y is going to equal the 1125 over x squared. And that's what I'm going to do right back up here. I'm just going to substitute it in for y. And then we could just simplify this. So this gives us 4,500 over x, and then plus 11,250 over x. We could distribute the 5, and then all finally simplifies into 5x squared plus 33,750 over x. Now we're going to find the derivative of c of x, and then ask ourselves, where is it equal to 0? It's undefined at x equals 0, but kind of like the last problem, x has to be greater than 0. Here we're going to multiply everything by x squared, so this is what we get. And then we take the cubed root of 3375, turns out to be a very nice number, 15. You could definitely use your calculator on that. And again, we use a second derivative test for extrema. So here's our second derivative. When we evaluate it when x is 15, it's a positive number, so we're concave up around x equals 15. Therefore, we have a relative minimum at x equals 15. Our dimensions then, x would be 15, y is 1125 over 15 squared, which turns out to be 5 feet. Now, it's not really asking for the cost, just when is it minimized. So we just say the total cost is minimized when x is equal to 15 feet and y is equal to 5 feet. But now there's a part B. Give a possible scenario for the cost function in part A. So if we go back up to the description here, it says the cost associated with the tank involve not only the material from which the tank is made, but also an excavation charge proportional to the product XY. So here's one scenario. We could say, if we have the 5 and then the 10 here, that could be the cost. So the material for the tank costs $5 per square foot, and the excavation charge is $10 for each square foot of the cross-sectional area of one wall of the hole. What I want you guys to do is just read this over, go back to the picture, and see if that makes sense. The material, so we're trying to find really like the surface area. And then we're going to take a cross-sectional area, which is going to come out as just like one flat rectangle, and then see if that makes sense. So read over that, go back to the picture, and do your best to interpret that. If you still have questions next week, I'll go back over that part of the problem with you. All right, and then let's take a look at 31. Now here they give you the figure, so just try to redraw it as best you can. There's my version of it, my attempt. So we want to find the volume of the largest right circular cone that can be inscribed in a sphere of the radius. So the cone that's in the middle here, we're trying to maximize that volume, make it the largest cone we can possibly have, or the cone with the largest volume. One thing we need to know is the formula for volume of a cone is 1/3 pi r squared times height. But I'd like to put this, notice everything in here has an x and a y. So the volume in terms of x and y, the radius of the cone would just be the x. That's like the circular base here. And then our height, which is right here, the height of our cone is y plus 3. So that's what I have right here. H is equal to y plus 3. So we need a helping equation. We need to get everything in terms of one variable. So that's what we're going to use over here. I'm just going to use Pythagorean theorem for this right triangle. So we're going to have x squared, this little right triangle, plus y squared would equal 3 squared. And then solve it for, in this case, I would normally say solve for y, but because we're going to square x, why don't we solve it for x? Because we're going to end up squaring a square root, which will go away. So we're going to do this. So now I want to get everything actually in terms of y. So v of y becomes 1/3 pi. X again is the square root of 9 minus y squared. We're going to square that, and then times our height here, which is y plus 3. So as we go through and simplify this, the square root goes away. We can distribute, multiply these two together, and that's what we end up with. All right, so we want to find the derivative, v prime of y. And this is what we get. So we can think of this just as a coefficient. So we simply just take the derivative of each term inside the set of parentheses. Ask ourselves these two questions. So what I did to begin with here is I just divided both sides by pi over 3. I rewrote this, factored out a -3, and then we can factor here. But because y has to be greater than 0, we don't use the y equals -3, just y equals 1. Then we can go through our second derivative test for extrema. Here's our second derivative. Evaluate it when y is 1. So that would still be negative. So that indicates we're concave down around y equals 1. We have a relative max at y equals 1. So we can go back, find the dimensions. Let's just go back to x squared plus y squared equals 9. Then x is equal to radical 8, or 2 radical 2 units. Y would equal 1 unit. So to finish this up, we could find the volume using the volume function that we just found here. So the max volume is 32 pi over 3 cubic units when y is 1 and x is 2 radical 2 units.